For this lesson, we're going to continue to be looking at the core concepts around the course, which is functions, and a very important concept, which is domain and range. It's one that's going to come up frequently throughout the course, and it also occurs quite often in subsequent courses, especially the advanced functions course. The statements which define domain and range are actually quite simple on the surface of them. Domain is the set of all possible values for the independent variable. Quite often, the independent variable is our x variable, and range is the set of all possible values for the dependent variable, which is quite often going to be y. It doesn't always have to be x and y, but that's certainly the most common configuration you're going to see. Now, this idea of set might be new to you. And so there are different ways that we can represent a set of values. And so let's talk about that now. One of the things that's most important or most defining or distinctive about sets is the use of this set notation, where we use a brace bracket or a pair of brace brackets to enclose things. And you can see my mediocre attempt at it there. It's obviously much nicer if you're doing it on a word processor or with some sort of computer graphics. So we can have just a list of values. So that's one possible way that we can represent a set. So you can see here, -4, -1, 3, 6, and 1. The numbers have varying deltas or differences between them. We've got a gap of 3, then a gap of 4, then a gap of 3, then a gap of 5. There's no particular consistency, and so there's no particular pattern here either. It's just a list of numbers. And what this is saying is that those are the only numbers in this particular set. Quite often we're going to be dealing with sets of numbers that are quite large, all the way up to sets of numbers that are, in essence, infinitely large. And so, for example, you can have a rule defining a set of numbers, and there's a couple of ways that we do this. Normally, you will choose one of these two ways of expressing your rule. You will either express valid values or you will express invalid values. You don't normally combine the two. So we either assert or we state where we're allowed to be, or we say where you are not allowed to be, but we don't mix them. So here is an example of saying where you are allowed to be. I'm allowed to use x values that are less than or equal to 2. Now you might be wondering about this kind of fancy looking R here. That means real numbers, and I'm going to give a brief rundown of the different number sets just so you have some context. This is probably something that you covered not in recent grades, probably quite a long time ago that you were introduced to different number systems. So real numbers, they represent basically all the numbers that we use commonly. Counting numbers, integers, but they also count things like fractions. They include non-repeating decimals. They include numbers like pi, numbers like the square root of 2, kind of awkward numbers that we can't represent as fractions. In this case, we're saying it's made up of all real numbers, but we're only allowed to include those numbers that are less than or equal to 2. Another way we can say is an exclusion, which is to say, okay, x is made up of all real numbers, but it's not allowed to be -5, that one particular number. And we'll get into some examples of when that occurs and why as we progress in the course. You've actually already had some experience with numbers or with locations that you're not allowed to go, and we'll be expanding upon that. So when it comes to number systems, I have this very old slide that I continue to use because it's a nice summary of it. If we start at the kind of smallest sets, we have the number 0, which is an incredibly small set. It literally contains that single value 0. We have the natural numbers, which was the first number set that people probably ever developed, and those are just counting. When you think of counting on your fingers and toes. Whole numbers is just the combination of 0 and natural numbers. Then there are the negative numbers. Basically take all the natural numbers and think about applying negative signs or going in reverse. Combine those with the whole numbers, we end up with integers. If you take one integer over another integer, like a fraction, so if I do something like a over b, where a and b are both integers, then I have the rational numbers. I don't want to get too far into detail. What are rational non-integers, etc. Then we have the irrational numbers. Irrational numbers are numbers that we might know already. For example, pi, which is this 3.14, and it goes on. There's no repeating pattern to pi. Or something like the square root of 2. If you put that in your calculator, you'll see that very much like pi, it just goes on and on and on with no discernible pattern. Actually, it's unfortunate. The first 4 digits there look like a pattern, but that 1414 does not keep going. It changes into other values. And then when you put all of these things together, you end up with the real numbers. Here's a more updated version of the same thing. Expresses things a little bit differently, but it shows nicely how different values fit within. So the natural numbers are nested inside the whole numbers. They're the same except for the addition of this value of 0. And then the integers are all the whole numbers, but now we consider negative versions of those as well. Then we've got rationals with some examples. They've phrased this slightly differently, the real algebraic numbers, and then they've also got another category called transcendental numbers. We're not going to worry about that. We're really going to be talking a lot about integers, even more about real numbers, a little bit about rational numbers, and we don't do imaginary numbers anymore. It's something I'd like to talk to maybe about with the rich class or the AP class, but we don't normally cover that in grade 11 anymore. So to illustrate this, it's always nice to have a diagram to go with these things. So here are some visual examples of what domain might look like. So here I have a number line. It starts at 2. You can see from the blue line overlaying it, it's everything to the right of 2, and it includes 2. So the solid dot means that it includes 2. And the way that we represent that it includes 2 is we use a greater than or equal to sign. And contrast that with the next example, which I have here, where x is less than -3. But notice that, first of all, notice the absence of the equal to. So that means it's less than -3, but it does not include -3. And the way I represent that on a graph, or in this case on a number line, is with an open dot. A slightly more sophisticated domain would include both of those. So if I put both of those together on the same number line, notice that the way that I've joined them is using the or. I'm basically saying it can meet this first condition, which is everything to the left of -3, or it can meet the second condition, which is everything to the right of +2, and it also includes +2 because of that equal sign. Even more sophisticated, here is, it doesn't look it at first. The number line is actually simpler than our previous example. It is all of the numbers between -3 and 2. It doesn't include -3, but it does include 2. We have a couple of notations here. You'll notice that I switched from using the word or to using the word and. The word and here means that it has to satisfy both of these conditions at the same time. And only the numbers between -3 and 2 satisfy those conditions. To avoid having to worry about appropriate use of and versus or, we actually have, when we are between two values, there's a preferred notation here. And I'd much rather you get comfortable with this. When I give you information, and quite often when the textbook gives you information, it's going to appear in this form. And it actually makes a lot of sense. It's saying that x is a real number. X is between, so you notice that I've positioned the x actually between the lower number on the left, the higher number on the right, and then I'm just careful with my signs. So the -3 is less than x, so no matter where x is, -3 has to be to the left of it, but the x also at the same time has to be less than or equal to 2. So no matter where x is, it has to be to the left of 2. And that only allows for this stretch of values between -3 and 2. A little bit less common, but could still happen, is in this case, you can see I have a bunch of consecutive integers. Now, it's important that they're consecutive. If there was a gap, if one of these dots was missing, we would just do them as a list. That first example I gave you of a set, which was just a list of numbers. But because we actually have all the numbers between 2 and 7, we could, there's not that many to write out, so we could actually represent these just as a list, 2, 3, 4, 5, 6, 7. Or we could use this another, maybe new to you, fancy notation, which is x member of this stylized z. And that stylized z represents the set of integers. And here I'm saying it's all the integers between 2 and 7, and it includes 2 and it includes 7. Technically, what I've got surrounded here in red, obviously to indicate don't do this, this is technically correct, but it's not a very good representation. So give a moment to think about why that is. I'm saying it's integers between 1 and 8, but it doesn't include 1, and it doesn't include 8, which forces it up to be 2 and forces it down to be 7, because we're not allowed to include 1 and 8, but we're only allowed to have integers. So really, why would we use this notation? Really, this is the best, especially if you have a lot of integers and they're all consecutive. And this is perfectly fine if you have a smaller list. That's pretty easy to just write out each and every one of them. Now we have some other ways, and let's get into actual domain and range. Those visual examples I showed you with the number line, those were all just domain examples. Now, you spend a lot of time, when we were in grade 10, we spent a lot of time graphing linears and even more time graphing quadratics. We are going to spend a lot of time becoming familiar with the idea of sketching all sorts of different functions that we look at in this course. One of those functions is the radical function. Now, the parent for the radical function looks like this, just to refresh your memory. It starts at 0, 0, it curves up. It's like a parabola tilted on its side, but it only has one part of the parabola to it. So that is what we call the parent function, y equals square root of x. Now, what is a sketch of square root of 2 minus x going to look like? I think in order to sketch this with the tools that you will have learned so far to this point, we actually need to rearrange that a bit. We need to put it into a notation that's a little bit more familiar to us to sketch out the transformations. So I'm going to take 2 minus x, and I'm first of all going to write it in a slightly more familiar order, which is to put the x first. But then I recognize that normally when we have operations, if we're trying to read transformations, we need to have a bracket, because that coefficient on x is a -1. So what I'm actually going to do is I'm going to factor that -1 out, but I'm going to factor it out of the negative x and the positive 2, and I end up with x minus 2. And now I can just read those transformations. This first one, that is a k value of -1, and that would mean that I have a horizontal reflection. You could do this in your head. Remember, the only thing we were asked to do here was to sketch. But I want to give a little bit of background so you understand where this is coming from and why I made the decision to rearrange this. If we take a look here, again, that's within the function, because the parent function was square root of x. All of these parameters, k, and then that must be p, that is p is equal to 2, because it's always x minus p. And so p equals 2, that is a horizontal shift. And in this case, it's a shift to the right by 2. So now let's take our sketch that we have here, and let's think about, well, what does a horizontal reflection look like? Just the horizontal reflection looks something like that. So I'm going to label that transformation number 1. And then a shift to the right by 2 is going to get me to my final form. So that means that whole thing has shifted to the right by 2. And so that now is transformation number 2. You can see that's a pretty rough sketch. It's not helped by the limitations of my ability to write with this tablet, but that is enough for me to be able to determine the domain and range. What is the domain of that solid green line? What x values am I allowed to put into that function? And in this case, this was a shift to the right by 2, which means this actually is at an x coordinate of 2. I'm allowed to have everything to the left of that. So first of all, it's x member of R. It's going to be real numbers, such that x is to the left of 2. And then the last question we ask ourselves, should we do less than or equal to? Remember the parent, am I allowed to take the square root of 0? And the answer to that is yes, the square root of 0 is 0. So that means this is a solid dot, and that solid dot is what moved over here, which means it includes 2. And so I am going to put a less than or equal to there. For the range, a little bit simpler actually to look at the range. Y is a member of the reals such that, and it's just everything above the x-axis, so y greater than 0. And we once again ask ourselves or remind ourselves that we have a solid dot there, so it's y greater than or equal to 0. And there's my domain and range using a sketch. Now, what about, and you can see I've got a blue background here. This is technically not required, but it's such a useful thing, especially for simple little problems like this, that you might want to put a little bit of time and effort into learning and practicing this skill. So I mentioned when I opened this, I said visualizing or sketching a graph is a good way to see domain and range. Algebraically, you might want to consider an inequality. We know the property of a square root is that we can only take, right, we're only allowed to take the square root of positive numbers, of positive values, and that includes 0. So if that's our rule, then what it means is whatever is underneath this square root sign has to be greater than or equal to 0. So we can rewrite that using what's known as an inequality. Now, I'm not going to do anything too advanced here. Just like an equation, I can subtract 2 from both sides because I'm trying to isolate the x. And so now I end up with negative x greater than or equal to negative 2. And this is where the only funny part of an inequality comes into play. In order to get x all by itself, I'm going to divide both sides by negative 1. And when you have an inequality, whenever you multiply or divide, so whenever I multiply or divide by a negative, we reverse the inequality. And that's it. That rule for when you're doing simple arithmetic, add, subtract, multiply, or divide, that's going to allow you to solve simple little inequalities like this. And this is actually much quicker and much easier than sketching out the transformations as I showed you on the previous slide. Negative x divided by negative 1 becomes positive x, which we want. Negative 2 divided by negative 1 becomes positive 2, which is going to be related to our answer. And then this greater than or equal to sign is going to change into a less than or equal to sign. And that's because of the reversal that occurred, because in this case I divided by negative 1. If I hadn't divided by negative 1, then I wouldn't have needed to reverse that. Okay, now when we talk about domain and range, sometimes there's the purely mathematical version, which I've shown you up until now. then you might be dealing with a real world problem, and you have to consider that in your domain and range. And sometimes on questions, I even go so far as to say this. I say, consider real world impacts. So in this case, this is a question you might have seen in grade 10, except for we've kind of modified it for the grade 11 course for dealing with functions, and specifically here for dealing with domain. You have 20 meters of fencing for this rectangular area. So before we even start trying to answer this, let's just write out what we know. We have 20 meters of fencing. So that means that if I do the entire perimeter, that's 2L plus 2W is equal to 20. Part A wants the area as a function of width. Now we can't start with that. So let's just start with the area the way you would have written it in grade 9 or even earlier. The area is length times width. That's the definition of area for a rectangle. Now, right now, we have area as a function of length and width, but we want a function of width, and I could have said width only. So how do I get rid of this L? And the way that I do that is I make use of this perimeter relationship. If 2L plus 2W equals 20, if we divide both sides by 2, we end up with L plus W is equal to 10. And then to get, now, and I'll explain why I'm doing this, to get L all by itself, I can subtract W from both sides. And I end up with this relationship, L equals 10 minus W. Now, the reason why that's useful is that I can rewrite my area. Remember, we wanted to get rid of this L. So what I'm going to do is I'm going to, instead of L, wherever there was L, I'm going to write 10 minus W, leaving the other W where it was. And notice now that the area is in terms entirely of W, which means I can actually use function notation now, and I can write the area as a function of the width. If I input a particular width, then it's going to output the area. So if I put a number in here for width, it will tell me what the area is. So that's it. Express the area as a function of width. That's done. Determine the domain of this function. Okay, well, that's interesting. Let's look at B. Now, there's a couple of ways that you could do this. Again, one way we could do it is we could come up with a sketch, or maybe we could make use of the fact that we're going to have a parabola here, because notice I've got a power here, W to the power 1 and W to the power 1, and when I multiplied those out, I ended up with a W squared. So A of W is 10 minus W times W. And we can immediately, just by inspection, it's already in factored form, so we can actually tell that the zeros occur when 10 minus W equals 0, or when W equals 0. And so that occurs when 10 equals W. And of course, this one occurs when W equals 0. And so if I put W on the horizontal and I put the area as a function of W on the vertical, I have zeros at 0 and at 10. And we can immediately see that that means that the axis of symmetry must go through 5. That's going to be the location of the vertex. I've got a negative W here, and if I multiplied that by this positive W, I'd have negative W squared. That tells me that this parabola opens down, and so it's going to look like that. Now, we could go further with this, and in some questions you will be asked. You might be asked, what is this maximum value, etc. But in this question, the question wants to know what is the domain of the function. The domain is the set of valid values for the independent variable. So W is your independent, And so the domain is going to be, what are the values of W? Well, W is going to be a real number such that, and then what can W be? W, here's the W axis. We know that W runs between 0 and 10, and it can be any of the values in between. So you might start with that. So it goes between 0 and 10, and it's anything in between. Now here's an interesting question, because we're talking about the real world. Oh, you know what? Actually, I'm sorry. I need to backtrack a little bit there, because we're talking about the real world. If we're not talking about the real world, then the domain on W, it's just a quadratic. It would be W is a member of R. But if we take a look at our graph, if we think about what that means, we know that the area of a rectangle has to be some positive number. So it's W member of R, so that W is between 0 and 10. I got a little ahead of myself there. And now ask yourself the question, should that include an equal sign, or should it not include an equal sign? What happens if W is 0? If W is 0, then you don't actually have a rectangle anymore. You just have a line. And then you would have an area of 0, because the line has an area of 0. If you had W equals to 10, well, that's going to produce the other 0. And so I would argue that the domain, considering real world situations, should be as written here, between 0 and 10, but it does not include 0 and it does not include 10. Okay, let's finish up with some more sketching, stating domain and range. Some really fundamentals here. Well, one of them in particular, one of them is the equation of a parabola. Here's a parabola. It has a vertex at 0, 0, so it's going to look something like that. So think about what's the domain for something like that. It's going to be X is a member of R. And is there any value that I'm not allowed to have? You can put anything in and square it. So the domain of a parabola is going to be X member of R, unless, as was the case in our previous example, unless you have some real world considerations to go along with it. The range, on the other hand, well, it's going to start off the same way. Y is a member of R, such that it's all the values above the x-axis, and it includes the x-axis. So it's going to be y greater than or equal to 0. Now, this might look familiar to you. It looks like it's got factors being squared here, but there's more than one of them. This is not a parabola. You've seen this before in your grade 10 course. It turns out that this is actually the equation of a circle. And I am not going to attempt to draw a circle here, especially not with this stylus. So I'll just put one in, a little bit of cheating there. And then remember, in the equation of a circle, that that's telling me that the radius squared is 25, which means the radius is 5. You might wonder, why didn't he write plus or minus 5 there? Because it's a radius, it's a distance. A distance is always positive. So that means that this is at positive 5. This point is at positive 5. Down here we have negative 5. And over here we have negative 5. Because on the x-axis and on the y-axis, those are the results from having a radius equal to 5. And so now when we write the domain for this circle, where am I allowed to go with my x values? You can see I've got points at x equals negative 5, but also negative 4, negative 3, negative 2, all the way down to 0, and then 1, 2, 3, 4. It's not saying the graph passes through the center line here. It doesn't travel along the x-axis. Remember that every point on this graph is made up of an x-coordinate and a y-coordinate. The domain is trying to get you to define what are the possible x-coordinates that will work with this equation, which show up on the graph. And it's going to be x member of R such that it goes between -5 and +5. X is going to be between them, and because it includes the values at the extremes, we use an equal sign. In this case, it turns out the range is exactly the same, y member of R, such that -5 less than or equal to y less than or equal to +5. And I believe that is it for this particular lesson. There is some suggested work from the current textbook. Notice for number 12, C and D, you're being recommended to use technology. If you don't have available technology, I would skip it. If you're looking for something that you can use online, free is something called Desmos. Finding that the stylus is particularly uncooperative with my writing today, or it's my hand. So I would recommend using something like Desmos, or if you've got a graphing application on your phone. And that is it for this particular lesson.